Now, what happens when there are additions to the soil? Materials that are added to the soil, such as decomposing vegetation and organisms, that is the organic matter, the O horizon, or new mineral matters deposited by wind or water. So these additions are made. Additions of humus is made to the soil horizon and the organic matter layer is formed. Now simultaneously we also have the losses. Now through the movement of wind or water or uptake by plants, soil particles such as sand, silt, clay, organic matter, these are all of various textures, and the chemical compounds, they can be eroded, they can be leached or harvested from the soil, altering the chemical and the physical makeup of the soil. Now, apart from the additions and the losses, I've told you that transformation takes place. Transformation, that is the chemical weathering of the sand and formation of clay minerals, transformation of coarse organic matter into decay resistant organic compound, humus, is formed. Here what happens? Dead leaves, they decompose into humus. And there are hard rocks into soft clay. It is turned due to transformation. Hard rock, due time takes, and there are different leaching processes, there are different mixing effects which leads the hard rock to make into a soft clay. And also you see that oxygen reacts with iron, rusting the soil into a reddish color. And translocation, it is the movement of soil constituents within the profile between the horizons, and over time this process is one of the more visibly noticeable as alterations in color, texture and structure become apparent. Here I have given a detailed information about the different types and the different types of additions and the removals that are taking place. Now, translocation within the soil profile is primarily due to the gradients in water potential and chemical concentrations within the soil pores. Now, there are soluble minerals, calcium carbonate, then the colloidal material, which are the clays, organic compounds, and iron. They move up or they move down the profile between horizons with water movement and help in translocation. And there are biological activity also that cause gradient in the chemical composition of water and air-filled pore spaces of the soil. So see here how the physical weathering is breaking rocks into small mineral particles. Here is a soil profile. This is a physical weathering generally takes place in the Arctic region in the cold climates, right? And chemical weathering along with physical weathering takes place in the more humid, in the more warmer areas. Chemical weathering dissolves and changes minerals at the Earth's surface. There is a complete change in the texture and the color. You see the change in the color? It's finally the weathering has dissolved all the minerals within and has given a prominent color to the soil profile. Now, the soil development, the US Department of Agriculture estimates that it takes nearly 500 years to form an inch of topsoil. That is less than 0.01 millimeter per year. So it takes such a long time to develop soil. The main processes that we will discuss today are fossilization, laterization and calcification, which are the three specific soil forming processes, and they produce the primary soil types. From fossilization, we get a soil, which is zonal soil, which is known as podzol. And from laterization, we get soil which are known as laterites. And calcification takes place in typical arid grasslands and shrubs, which gives the Chernozem soil. And glaciations, they are typical of waterlogged tundra region. Now, the main process in the formation of podzol is podzolization. Now, it is a complex process in which the organic material and soluble materials, they are leached from the A horizon and E horizon to the B horizon, and it involves the mobilization and the precipitation of dissolved organic matter together with aluminium and iron as they leach down from the A and the E horizons to the B horizon. Now, through this process, what happens? The overlying alluvial horizons are bleached. So, we have a white grayish layer. You can see in a podzol soil, there is a bleached layer because from the alluvial zone, the minerals have been leached down to the next zone where it has been alluviated. Now, translocation has meant the alluviation of clays, humic acids, irons and other soluble constituents from the A and the E horizon. And what happens? There is severe leaching, leaves the upper horizon virtually depleted of all the humic acids in the form of soluble salts. Now, these leached material from the A horizon is deposited in the B horizon as a humus-rich band, a hard layer of sesqui oxides or a combination of two. Now, you see here the profile. Here, there is leaching. This is the zone of alluviation, and then this is the zone of alluviation where all the minerals have come, and we found this, okay, of the sesqui oxides. And this podzolization is very much active in cool weather and when there is abundant precipitation. You see, it develops in cool and moist climates under pine forests. There are acid falls from the pine and which makes the soil very much acidic. And they are typical of the colder portions of the humid continental and subarctic climates. And the E horizon, I've told you, is very much leached and basically composed of a light colored layer of sand, which is known as the bleached zone. Typical ashy grey layer left from leaching of sesqui oxide is apparent in this podzolite soil, and the upper portion is stained reddish from the accumulation of sesqui oxides, and the profile gets lighter in color as the depth increases. Now, the next process is laterization, and it is derived from the word later, which means brick or tile, and was originally applied to the group of high clay Indian soils found in the Malabar hills of Kerala, Tamil Nadu, Karnataka and Maharashtra. Now, it refers specifically to a particular cemented horizon in certain soils which has become dried and become very hard like a brick. So, what happens is that these soils are massively impregnant with sesqui oxide, iron oxides, and they are also called latter salts and oxysols. So, this process is known as laterization. Now, unlike podzolization, laterization operates most favorable in warm and humid tropical climates where there is abundant rainfall and continuous high temperature throughout the year. Another thing is that the rainforests of tropical areas are favorable for the process of development, and the parent material having sufficient iron-bearing ferromagnesium minerals which on weathering release iron and congenial to the development of laterites. In the early slide, you have seen this process. This is the soil profile of a typical laterite process. Now, this profile is no distinctive soil horizons are developed, and in the absence of silicate colloid, the soil tends to be firm and porous rather than sticky and plastic, and they are transmit water readily. And laterization results in very low soil fertility because bases are not held in the soil and humus is lacking here. Now, I've already told you where this process is dominant. It's mainly in the humid and where precipitation is very much high. Now, the last process that we'll be discussing is calcification. Now, it is the pedogenic regime of climates in which evaporation, on the average, it exceeds precipitation. Now, calcification is associated with a continental climatic regime with a total annual precipitation and with a tropical wet-dry climate. And grasses which use these bases restore them to the soil surface. Grasses add their matter to the soil and again it comes back. Now, calcium carbonate brought upward by capillary water films and evaporated in dry periods is precipitated in the B horizon of the soil in the form of nodules, slabs and even dense stony layers which are known as calicum. And there is microbial activity which is very much restricted and humus may abundantly distributed throughout the A and B horizon. Now, this is the profile of calcification, a Chernozem soil. Here you see there is a zone of excess lime and here capillary rise in dry weather is taking place because of this capillary rise, and here we get much of calcium carbonate. Chernozems, they develop in cool climate. This is the tropic, this is the profile. You see, there are distinct layers and we see that there is deposition of calcium carbonate here, the white portion. You see, there is excess of lime deposition here because of the capillary action. Now, this occurs in warm and semi-arid environments, usually under grassland vegetation, and the soil tends to be rich in organic matter and high in soluble bases. The B horizon of the soil is enriched in calcium carbonate, which is precipitated from water moving downward through the soil or upward movement of capillary water from below. Now, to end with, I would like to say that you can identify him, Franklin D. Roosevelt. He was an American president, a statesman for, a major term, and he once remarked that the nation that destroys its soil, it destroys itself. He was the one who knew that soil was the most important natural constituent of the natural environment. We cannot deny soil. And it is not that the land on which we are standing now is a soil. Soil needs time. There are different factors that are acting upon it. There are different processes that are acting upon it. And these processes vary from one place to the other place. And they give separate identity, they give separate profile, they give separate physical, chemical composition of the soil profile, and it varies from one place to another place. So my dear students, I tell you that when we are going from one place to another place, if we have a chance to look at the different types of soil, just go and see and just go and watch that how that soil has formed. It is not only a time, it is not only a factor of a few days or few weeks or few years that has led to the development of the soil, but a long time, a time that makes the soil different from one to one. So I say that the nation that destroys its soil destroys itself, as told by Roosevelt, is very much true. And the development of soil, as we have seen, that the factors and the processes together, they make a soil profile, and the soil is distinguished from one place to another place. So students, today we saw that climate, organisms, parent material, relief and time are the major soil factors that help in the development of soil, and the processes such as fossilization, calcification, laterization, glaciation, which we did not go into detail, and salinization, eluviation, weathering, leaching. These all are the processes that are constantly acting upon the soil and making the soil, giving the soil its most unique characteristics, which is different from others. So, the nation that destroys its soil destroys itself. It was very much true, which was said by Franklin Roosevelt long years ago, and we owe Dokuchev, Jenny, there are many other scientists, Hilgard, Murbert, Joff, who were the soil scientists who helped soil to be incorporated as a natural science, and the developments that were made further for the study. Thank you.